Thank you all. Thanks to Mr. Tag and Tacen. This event has been fantastic. Very happy to be here. So I've been working at the Urbit Foundation for, the past handful of months. Prior to that, I was at Tlon for a few years. And we have been focusing a lot on the Urbit network. Myself, Robnus Rickford, Norsa Torin. Really a simple and straightforward set of goals that we want to accomplish here. There's a lot of great things about Urbit's network. But outside of maybe the first one, it's not exactly famed for either of these properties. And networking is hard to talk about. It's really a strange thing. It's quite different from computation. And you construct functionality from a very disparate set of, probabilistic behaviors, right? Fundamentally, it's insecure, it's unreliable. You're just sort of shouting into the void. And talking about how to wrangle it is bringing together many, many different pieces and then kind of squinting through the overlap. And so I wanted to start at the beginning and try to recap what we're trying to accomplish with the Urbit network. Examine some of the other sources of inspiration that we'll go into in a fair bit of detail, some of the history of networking itself, and then take stock to see if we are accomplishing what we're setting out to and if we're getting what we're paying for, because we're paying quite a bit. So of course, you can't talk about fundamental Urbit technology without going back to Urbit's original public introduction to the world. It's all here in this post. And I'll just go ahead and read the quote. I call the Martian network architecture source-independent networking, or SIN. In almost every way, a source-independent network is exactly the same as today's insecure, unreliable packet network. However, there is one difference. To make IP source-independent, remove one 4-byte field, the packet source address. Now, to be completely honest, I have puzzled over these lines for years, because if you take a look at an AIMS packet, not only does it not remove the 4-byte IP source field, it adds an up to 16-byte Urbit source field. And so what's being said here is subtle and not particularly clear, possibly aspirational. One more bit to quote. Strangely enough, some insight into Martian networking can be gleaned by reading this Wikipedia page, content-centric networking, or watching this Van Jacobson talk, a new way to look at networking. VJ, in case, oh goodness, there are different slides. I will get that into my head shortly here. VJ, in case you're not aware, is a god in human form. When I saw the latter, I thought, that bastard had my idea. Bastard was not actually the word. It was a worse word, illegal, in fact, in many states. But of course, any truly Martian idea is far too simple to be original. Fortunately, VJ did not have my whole idea, just the network part. And as you will see, this quote, while hilarious, is actually harder to interpret than the previous one, because we'll talk about what content-centric networking is, and then we'll talk about what AIMS are. And the degree of overlap is technically present, but incredibly remote. So I will try as quickly as I can to recap this video. This was a talk that Van Jacobson gave at Google in 2006. Van Jacobson is most famous for writing traceroute and basically making TCP scale. He's authored a wide variety of congestion control protocols. In the talk, he's very complimentary to TCP IP. And it's an expression of humility because when they tried to scale TCP above very small networks, it just completely fell over. It was a total disaster. And like the great man theory of history, computer science and network architecture rides on the backs of a very small number of people, and Van Jacobson is undoubtedly near the top of that list. So in the talk, he gives a history of networking and frames it in such a way as to make his new architecture compelling, deterministic, unavoidable. It's very compelling. I don't know if it's right, but it's very compelling, and I'll see if I can recapitulate that for you. The generation one was wires. This is circuit switching. This is telephony. This may, if you've studied much networking or done much reading on the history of the internet, this may all be obvious to you, but it was not obvious to me. Some properties of telephony, I should say. The first thing that you need for a circuit switched network is that you need wires everywhere, so the capital costs are unbelievable. And you can't make use of them until they are fully connected. The revenue in such a system comes exclusively from dynamically constructing a path through wires that you actually have. And this is what seemed to me a subtle point, but hammered very heavily in the talk. Calls were the product sold to the marketplace by the telephone network, but they were a side effect of the actual logic of the network itself. The logic of the network, everything about the entire system was just about building a path. And then once you had a path, you could use the path for anything that you could think of, and the only thing that people could think of was calls. But they were a side effect. And a telephone number, which looks, for all intents and purposes, like a name or an address, was actually a program. The original 4-digit numbers were two-dimensional coordinates on a 100 by 100 grid switchboard. And so you dial 1, 2, 3, 4, and you go to, column 12 and row 34, and you hook up the wires. The telephone number is literally a program controlling the system that builds paths. And this system had substantial problems when it was used for anything other than telephone calls and dynamics that trended toward monopoly. Path building is non-local. You need global knowledge of the paths, of the links that exist and their status. You have to schedule centrally. The reliability is terrible. A call fails if any link in the path fails. So as the system scales, reliability decreases exponentially with the number of links. And then, hilariously, when talking about data networking, incredibly high setup costs. You can't use the path until it's wired up all the way end to end. And I love this. So again, this talk is from 2006. And he says, if transcontinental setup time is 100 milliseconds and you have a gigabit link, by the time you've set it up, you've wasted 12 megabytes. So this is not practical for networking at all. You'd have to fetch a 12 megabyte web page to use the network at 50% efficiency, and there's no web page that's 12 megabytes. It's pain. But in general, you can't do what you want to do with data networks with a system that has setup costs like this, because you have to send a lot of data to make it worth the trouble of setting up the link. But if you make it slow enough, it doesn't matter. And this is why the phone company loved and was wedded to ISDN, which was 64 kilobytes. At 64 kilobytes, setup costs don't, 64 kilobit, sorry. Setup costs don't matter. But this was the entire world, and it framed everyone's thinking. If you asked anyone, up until the 60s, networking simply is telephony. And all of the research that was done anywhere was focused on dealing with these high setup costs. And now I'm just, as a point of order here, I'm stealing his stuff. I wrote the slides, they're his points, I'm recapping the video. I'm not gonna say, in every sentence, Van Jacobson says X, Y, Z, but if you have a problem with any of this, it's not my problem. Generation 2, instead of focusing on the wires, focused on the endpoints. This is packet switching. It was proposed in the 60s, first published in a RAND Corporation paper, and the idea is incredibly obvious to us now. It's hard to even see the breakthrough that it was. But the idea was simply to take the wires as given. The telephone network already exists. All of this capital cost has already been extended. There is a path, somehow, from one end to another. And if you split the data into tiny pieces, you can share that path. You can't monopolize the path like you would in a circuit switch network, but you can share it. And then you can use transitivity to make the network somewhat autonomous. And that is just really two quite simple things. You put the endpoint addresses in the data, and then when you receive a piece of data, if it's not for you, you try to send it on. That's it. Everyone thought this was insane. This can't possibly work. What's more, that's not a network. He says the entire staff of Bell Labs released a statement saying this can't possibly work. It ignores everything that makes the phone network work. But the director of ARPA, Licklider, I think, he liked the paper, and he commissioned such a thing to be built. So again, ARPANET was built on top of the phone network. And to anyone experienced in networking, it just looked like an absurdly inefficient way to use the old network. It's not a network. It's just this crappy overlay thing. The data the data is redundant, right? Like you could figure out who you're talking to, just because you have the link, but instead you have all of this extra overhead. You're wasting data, putting the addresses on the packets. But that property, that it was a pure overlay, that it didn't depend on the underlying layer, it made it completely agnostic to what was underneath. It made it so that it could actually work over any kind of link. And fundamentally, it's changing the point of view. It's looking at the endpoints and it's abstracting over the path. It was a huge success. Everyone wanted one, and so immediately you had a proliferation of incompatible proprietary packet switch networks. If you're like me and you took some networking classes, CCNA kind of stuff, IPX comes to mind. I know there was others. Maybe somebody else knows, but in any case, there was lots of them. Apparently all the branches of the military built their own, and they all worked really well, but they were all compatible. The paper was in the late 60s. ARPANET was built in the early 70s. By the mid to late 70s, Vint Cerf realized that since packet switching abstracted out the topological details of the network, if you just put a common header on the packets, a shared addressing scheme, common encapsulation format, you could concatenate networks together. For some reason, the name Catenet just was not a marketing coup. But they built it, and it became the Internet Network Protocol, and yeah, the rest is familiar history. But there are some interesting notes. So in a packet switch network, reliability increases exponentially as it scales up. Each time you add another link, you're adding redundancy to the system, another pathway that a small piece of data can flow over. There's no link setup cost. And it's bandwidth agnostic. It works as well over a slow link as a fast link. It does not require a hierarchical topology, unlike the phone network. Centralized scheduling is NP-hard. And the way you solve an NP-hard problem is that you restrict it to a subdomain. Centralized hierarchical routing model made scheduling tractable for the phone network, but it wasn't necessary at all. There was no central view of the network. And so those were those first three bullet points, those were the three problems that were known, the goals that were trying to be met in designing this new system. They got the fourth for free. By virtue, the same adaptive routing mechanism that lets you route around failure lets you start sending packets from day one without central configuration, because the address is in the data. You get a packet, you don't know who it's for, you try to send it on. You need an upstream gateway, you need, some kind of other node. Let me see if So as a sort of another meta point of order, in the talk, Van Jacobson characterizes this as the network entirely, hooking itself together fully autonomously. I think anybody who's done much of anything with IP knows that that's euphemistic at best. But I do think that it's an accurate representation when it's compared to the prior model. The prior model is physically running cable. It's punching down a block. It's centrally registering the existence of you implicitly by virtue of the fact that there being a path to you. Whereas in the IP network, you just need an address. And so IP, and especially TCP/IP, were so successful that they entirely changed the world. Everybody knows this. Before there was no internet. Now there was an internet. Outlook unclear. But that's not the success disaster that he means here. This system was modeled and built in a world with few machines and many users for each machine. There wasn't really data on the network to speak of. The primary use case that was envisioned was remotely using computational resources. You have, we're in Wyoming, but the University of Arizona has a computer that fills 15 rooms, and we'd like a couple, flops. And maybe, the result that would be, printed out could be loaded back into Punch Deck and sent back to us back over the network. But the data volume is tiny. The model is communication between machines, two-party conversations between machines. Now here's his list of the problems with the packet switch world. And I don't know that our list would be the same, but this is interesting. Connected is a binary attribute. Oh, thank you. The internet is one thing. You can either talk to it or not. Connecting is a heavyweight operation, so I said you just need an address. Of course, we'll pretend that doesn't exist just for this portion of the talk. Not only do you need the address has to be topologically stable. to be able to percolate through the network and be addressable. And that, as of 2006, he says was on the order of hours. So you can't have a viable short-lived connectivity without a lot of infrastructure between you to make that work. To this day, the network absolutely hates things that move. IP mobility is a joke. The only way mobile phones work is that your provider pretends the entire world is a LAN, emulates everything in software. The IP that your phone is running is actually like 15 layers of overlay, and it's. But this is fundamentally true at the base models, and lots of things compensate on top of it. And then the base model itself is totally fine with broadcast, but all the transport protocols we use over it don't have any way to make use of broadcast. And this has only gotten much worse since he gave this talk with the proliferation of wireless, which is, fundamentally physically a broadcast medium, and all anybody does over it is have conversations. So I looked and I couldn't find statistics updated for today. In 2006, he says 99% of internet traffic is retrieving named data. Web pages, email messages, things of this sort. And it's quite possible that that number has gone down significantly because ubiquitous network security is almost exclusively modeled as conversation. So depending on which layer you're going to consider to be the network, even if your sort of application level patterns are still retrieving named chunks of data, that's being tunneled not just at the IP layer, but at higher layers through a conversational medium. But anyway, it was quite surprising to me. He said over 99% in 2006. And of course, acquiring content by name is not having a conversation. That is data dissemination. And so this is the shape of his presentation. And the point of it, right, is framing the success of packet switching over circuit switching as this abstraction, which it clearly is, taking things that were implicit in the topology and making them explicit in the data, and proposing that 20 years ago, the future of networking is dissemination, which can model a conversation somewhat awkwardly. Of course, you can make this work in either way. So everything that we do right now, browsing the web, anything like that, is layering dissemination over a conversational protocol. And let me check in here. That has problems that I'll get to on the next slide. I don't know why I laid this out like that. And so conversation over dissemination is inefficient, at least when it's done in a naive way. But dissemination over conversation makes the network blind to what you're actually trying to do. It can't help you. All you're doing is blasting data along. So when we browse the web, for example, the channel is secured and not the data. The example he uses, the SSL connection to his mail server does not help with spam. It's just in very clear, obvious terms, completely a layering violation. The network cannot help. Applications and users have to perform plumbing to translate from the data they want to the server they need to connect to. And then it's inefficient because the same data in the network bound for different destinations, the network is also blind to that. He says he got a chance to look at a core internet router downstream from NBC during the 2006 Olympics. and there were 6,000 copies of the same video frame of, what's his name, Bodie, the New Hampshire skier, you know, hitting the pole or whatever it was that year. But it was a huge congestion problem. The router's dropping packets like crazy, and this is ridiculous, right? It's public data, everybody's asking for the same thing. There's a layering violation here. The network can't model it. So what is his model for dissemination? Data is requested by name. Data has a name, not a location. Names are arbitrary, so they can be meaningful. This is opposed, or rather, strictly a superset of content addressing. Content addressing is to name something fundamentally by itself, usually by a cryptographic hash of itself. This has very nice properties. We can coordinate on what the name is without any sort of namespace in any real sense. There's no upfront coordination and there's no ownership of the data. It's just sort of a flat world where objects exist. And it's trivial to validate the binding between the name and the data, getting ahead of ourselves just a little bit. But it has terrible ergonomics. It doesn't encode any sense of locality. And in practice, anytime you're using a content address system, you have to build a layer over it for meaningful names, and then you have to authenticate the binding, and you're right back where you started. He argues, and I think convincingly, content addressing is useful in specific sort of narrow use cases, but it's a poor interface, and it's a mistake that many projects subsequent to this one have made to make content addressing the base layer. So data, again, is requested by name, not location. A request can be broadcast over any media, can be sent to anyone, and anyone or anything that has the data can respond. So at this point, we've started to close the loop back to the original Moron Labs post. Integrity and trust are derived from the data itself, not from the channel. So this is one possible interpretation of deleting the source address. It's not meaningful where it came from. What is meaningful is what it is. You have to be able to identify what it is from the data itself. And in a model like this where you can ask anyone for anything, anything that moves bits in space or time can and will be used to communicate. You can put hard drives on a plane, you can put hard drives on a truck, you can distribute data preemptively, opportunistic transport. And of course, when you think about those things, this is done all over the world. This is done today very much so. Whatever, peripheral Comcast office is closer to me probably has a rack in it full of drives, full of Netflix content. But the retrieval of that data doesn't really happen in the network in any meaningful sense. I talked to Netflix's servers on EC2, and they geolocate me, and then maybe they even authenticate on the side with the CDN node that they've paid Comcast for this peering relationship, and then they give me, finally after all of that, some session scoped identifier that lets me go and get that data from them. But all of that could simply be in the network. So if you communicate your intent to the network, if that's legible in the data, the network can do more for you. Well, this one's particularly interesting. A request-response topology. Request data by name, get a response that you can authenticate, matches that name, has that name. This allows fine-grained control of incoming traffic for quality of service. Now, everybody knows that, the network core is very fast, it can hold lots of data, and it gets slower as it gets out to you. And so congestion happens at the transition from a fast link to a slow link, not the other way around. On your home network, you have control over what you send and how fast you send it in what order, but not what you receive. You have zero control over what data gets prioritized. Now, that you could build an ad hoc protocol and the ISPs could deploy it, and then you could sort of negotiate with the ISPs, I want my video call, to trump my kids, Disney Plus. But there's not a huge incentive for the ISP to go to all the trouble to build that. And so, mostly things kind of work. Sometimes they don't. And there's not really a good option in the existing protocols. But when you are requesting data by name, you're in control. One request equals one response. The response is going to follow back the request. So the order, the rate, prioritization, all of that is in in your local control because it's request response and it's a poll-based model. And then, of course, if the name of the data is legible to the network and lots of people are requesting the same thing, then that can be handled very efficiently. You sort of get a multicast effect for free. This is yet another thing that was probably slightly more compelling in 2006 than it is today. Most security protocols, again, are conversation-oriented, and HTTPS is everywhere. I don't think that's a necessarily mathematical result, but there's no question that group encryption protocols where we will have a shared identifier as opposed to two-party or group encryption calls where each of us have a paired identifier, they're less common, they're more complicated. It's definitely worth calling out as something that changed in the last 18 years. So now we're getting to, pretty familiar properties. This kind of data dissemination model requires that the data be immutable because there isn't a path. It doesn't really have a lifetime. It can be stored anywhere. It can, traverse any link. It needs to be referentially transparent. There's a name for the data. The data has that name. Those things don't change. If you need to produce a new version of a piece of data, you supersede the old data. You do that under a new name. I'm sure this is very familiar to everyone here. Interestingly enough, in his model, and this is something that we should think about, but we haven't done in any meaningful way yet, there's two layers of authentication. There's basically a mutable alias layer, so a well-known name, where the binding from that name to data can actually change. And that's expressed as a binding from a generic name to a specific name, and then a binding from a specific name to a piece of data. And his example, he asked the network for newyorktimes.com/today, and he gets back a response packet that has two message authentication codes on them and a full name that includes the date. Whoa. Oh man, now you're going to see all my slides ahead of time.
Go faster so we don't read them.
Yeah, I wonder if the battery's dead. Does this work better?
Can you use your computer to go back slides?
No. It's not even plugged in, it's just for me. Whoa.
There you go. Amazing.
Look at that. All right, so that's the talk. I've already made this point, basically. His framing of the history of networking and the future of networking is that what has been successful is to take things implicit in the link, in the topology, in the conversation, and make them explicit in the data, abstract over the details of what is underneath it, and each new step of doing that unlocks new capabilities. So this talk, again, it was given 18 years ago. It was given to the right people to make this happen. In the intervening time, Van Jacobson was working at Palo Alto Networks. He founded the content-centric networking project. They built software. They published specifications. Palo Alto Networks was acquired by Cisco. Van Jacobson left Cisco. He got a National Science Foundation grant. He started the Name Data Networking Project as a fork of the content-centric networking project. There's 20 universities involved. So I'll start at the bottom of my list and work my way up. Name Data Networking is a fascinating project. It has produced massive amounts of very interesting resources, but it is very clearly stuck in a research trap. Pick any computer science tech buzzcode that you can think of and Google your buzzword and NDN, and I guarantee you will find a paper. I just don't know how else to say it. Some of them are really good, and a lot of them are just, some Joe Schmo's master's thesis. I'm sure Joe's a good guy. And the rest of these are basically my guess. So I don't think that the benefits are really worth switching if all you're going to do is lay conversations over the top of a data dissemination protocol. And everything that exists at this layer is conversation oriented. I already made the point about security, right? That has, if anything, gotten more difficult in the intervening time period. Even something that you'd think of as a group protocol like Signal doesn't send the same message with the same key under the same identifier to everybody in the group. And I'm not a cryptographer, so I'm not going to promise that you can get the same properties by doing it in that way. But I just suspect, quite frankly, there hasn't been a need, and so those protocols in that form haven't been developed. You can always come up with a naming scheme for things and always share some amount of derived, in ratchet, hashed data, whatever. There's got to be some degree of multicast possible in that kind of protocol. But it doesn't really exist. You can do a much dumber thing, which, jumping further ahead, I think we will, which is just, have people in a group, there's a key for the group, you rotate the key periodically, kick people out of the group if they cause trouble. But, that's better than a lot of things. That is certainly secure against the underlying network, but the trust model that's sort of shared in the group is very high. Another thing to call out about security, things like Signal, I believe the noise protocol framework as well, OTR before Signal, they really liked this idea of deniability. And so as the protocol would ratchet forward, you'd actually leak the old key material into the stream. So after some number of messages, anyone who observed the message could have forged it. And this is like really compelling if you're worried about a journalist under some oppressive regime. It's amazing that's always the example they use. I don't know, maybe the journalist should have moved somewhere else. I don't think it's the most compelling feature for a security protocol, but more importantly, Urbit's really never been built to do deniability. Urbit does pseudonymity, and the association between the data and the identity is strongly attested to. If you want deniable communication, use another pseudonym. We got a whole 128-bit address space of comments, go nuts. More obvious, similar to the protocol layer, to really take advantage of data dissemination, you need new application paradigms. right? Everybody is a publisher now, right? Conversations are derived through this, mutual dance of publication. And it's a really different way of thinking about applications. But if you don't factor your applications in that way, there are applications that are factored in that way, and they would get an advantage, the web browser, for example. But in general, you kind of have to turn your thinking inside out to write applications that way. So I would propose that that's also a big reason this hasn't taken off. And then finally, and this is pure rumor, my understanding is that content-based networking protocols are fairly ubiquitous inside big tech. That Google uses them, and Cisco uses them, and Netflix probably uses them, to manage their CDNs that are distributed all around. And so I think a big part of this is just the overall incentive structure of the internet being totally screwed, and nobody can ship any new protocols regardless of how good they are. But, like I said, it's conjecture. Maybe it's a bad model. When we look at NDN from Urbit, right, we're coming all the way back around, the inspirations are obvious. I'm sure there were other sources of inspiration as well, but Urbit is built for this in some very concrete way. We all know about the referentially transparent namespace, but also we have some nice properties that constrain the problem and make it easier. We have a node model, we have a PKI. In NDN, the PKI is totally abstracted over, right? You put some kind of like certificate identifier on the packet, and then there's some other way to go and get a certificate, and maybe we'll do a web of trust model, and this is all familiar. By virtue of having a node model and having addresses, we don't have to dive right into content-based routing. The NDN model is nodes have links. It knows that it's got a Bluetooth radio. It knows that it's connected to Ethernet. And it starts out by just blasting out requests over every medium. And it dynamically builds up a forwarding information base, as they call it. And then it tries to do path-based prefix routing. And then you need protocols on top of that to, your BGP or OSPF kind of protocols to, share and negotiate and authenticate routes. And all of that's awesome, and maybe we'll do it someday, but it's hard, and we just don't have to do it now. We have a node model. Every name in the namespace, every path starts with a ship. The ship is a first-class routable identity. So we can just collapse the problem space way, way down. The need for new application paradigms it's no problem at all. Like, we're here. That's table stakes. But conversations are kind of nice. Like, it's just a very natural way to think about communication. We talk about a peer-to-peer network, and like that just sounds like a conversation. And so if the model pessimizes conversations too much, it's not going to fly. And you can generalize that and just say, what's not nice about the conversations over NDN. We'll get to it in some detail, but in general, it's the request pull-based semantics. You really want to be able to push a piece of data out to somebody, get their attention. You also just want that for change notifications. And then the other thing that I should mention, as far as the namespace is concerned, is that NDN is sort of equivocal about referential transparency, not just in the way that I mentioned earlier, where there was like a generic name and a more specific name and multiple levels of attestation, but they're also really attached to this zero configuration story where, it would have been nice actually, but I'm here in the room and there's a projector and the projector is broadcasting itself as a name, and I can just, connect to the projector, but that's not a globally routable thing. That's not there's not going to be a trust root that I'm going to be able to discover for that thing. So they end up with a kind of two-tier system where there's some names that are locally scoped and some names that are globally scoped. There's some names that are referentially transparent and some that aren't. And in Urbit terms, it's just sort of mostly questionable with a couple of exceptions that I think we'll get to. So, this spring we shipped Finet. And Finet, it is not at all wrong to think of Finet straightforwardly as named data networking on Urbit. It is a request response protocol. It uses the namespace. You issue a request that is a path in the namespace. You get a response that is a signed binding of the path and the data. The data is, what we call a page, an arbitrary marked noun. So it has a tag on it that gives you some kind of hint as to what type of data it might be, and then any noun. And we're using this drives OTA upgrades and has since May, I think. Yeah. And it's highly cacheable. When you get a request, if it's for a packet you haven't produced yet, you actually produce the whole batch, a whole window of packets around that, and you eagerly push that out to your runtime and subsequent requests. Not only do they not hit the event loop because they're pure reads, they don't have to be logged to disk, anything like that. They actually don't even hit knock. It's a hash table lookup. But it's incomplete in some important ways, and it's really expensive. So this was the right decision to ship something, but it's an obstacle. Finet, request and response packets, this is dissemination over a conversation. It uses the same framing as AIMS, and we'll talk about AIMS soon, but that means that there's a source and a destination address and intermediate nodes. They get a request, they have to rewrite, or have a response, they'd have to rewrite the metadata for each destination that they're going to send it to. It's also not really an independent protocol. The routing is completely parasitic on AIMS. If you couldn't talk to somebody over AIMS, you can't talk to them over Finet. So those are the things that are incomplete about it, kind of below the line. And then above the line, you can't really use it for too many things. The basic model is that it's public data. So you could roll your own encryption and put ciphertext in your namespace, or you ship public data, source code for base, source code for apps. That's pretty good public data. Maybe you could argue that like the group's contact profile thing, that should be public, maybe. It's effectively public inside the network, but there's still a difference between public inside the network and public outside the network. It's hard to think of too many other things where you're like, oh, sure, yeah. Anybody on the path, have at it. And then, even if you ignore that problem, and the problem there basically being we don't want to force user space devs to roll their own crypto, your patterns of using it from user space are fairly limited, and initially were very limited. And so this probably deserves a little bit of a tangent. But before I do that, let me check how I'm doing on time. Holy crap, I'm doing terrible. Long story short, the main job of the Urbit kernel is to guarantee referential transparency. If you let apps do whatever they want with the namespace, you can't guarantee referential transparency anymore. Right now, it's really locked down. We want it to be much less locked down, but they have to be well-defined patterns that are legible to the kernel so it can still maintain its invariance. All right, let's, also it's really, really, really freaking expensive. So this was, I just ran this and copy-pasted the output this morning. On a fake Zod, it's an M2, that is a fast machine, and what I am signing is the number 0. It took 4 milliseconds to sign the number 0, and 6 milliseconds to sign and then verify the number 0. In Finet, we sign every message, and then we sign every packet. So it works great if the data is going to go out to a lot of people, you've amortized the cost. You don't have to log events, right? Requests come in, they're pure reads of the namespace, they parallelize for free once Ares is here and we have a multi-threaded runtime. It'll be great, we'll take advantage of this, but it's really, really heavyweight. So I'm going to pick up the pace. To make it less expensive, we're going to go from we sign every message to we sign most messages. Content addressing, for when it's useful, needs a special carve-out because that's trivial to verify. There's no reason to sign it. When I get to aims, I'll talk about another carve-out. And then we don't want to sign every packet. Packets aren't that important. We have to be able to validate that a packet's part of a message and its position in the message, and that's it. A Merkle hash is great for that. There's a new version of the Blake hash, Blake 3. It is a tree hash. There is a serialization of it for a verified streaming use case called BOW. We have to tweak it a little bit for our use cases. I really wanted visual aids, but I don't have them, so I'm going to just keep going. It's a tree hash. It's not rocket science. To complete Finet, remove the conversational envelope. Requests are anonymous. They don't have a source. It's just a read for a path. You're still reading public data. You route requests statefully. If you get a request that you can't satisfy and you are configured to forward it, you remember the request and you forward it on. Later on, when you get a response, you just return it to whoever requested it. So this is very much like a sort of stack discipline, function call discipline. Think of requests weaving their way through the network, leaving breadcrumbs, and responses coming back, eating the breadcrumbs. Those are the short term. And the long term, subscription reform. User space publication models that are legible to the kernel, put lots of data, and the namespace needs group encryption to be useful for general data. But even so, it's still not complete. We do all of those things. We cannot shift all of our communication to this model. Frontier discovery. What's the latest version of something? Long-lived requests. You don't want to pull all the time. And then after some interval where it doesn't even, they're not going to keep your long-lived request around. It's been too long. You need notifications. Consider a chat channel. It might be quiet for months at a time, but you actually want to hear it pretty quickly once somebody posts in there. So like an exponential back off, long pulling kind of thing, it's not going to work. There are designs for these things. They're out of scope. Aims. Gonna keep going fast. Everybody knows aims. This is how aims is always described. This is true in a sense. From user space, if you squint and forget about some of the things you can do in user space, it's true. It's not really exactly what aims is in its own terms. Aims is absolutely Martian networking. We don't process a packet differently depending on where we hear it from. There is a source and destination in there. We use them to look up keys, basically. So it's somewhere in between. It's not TCP, right? The semantics are not session-based, they're not connection-based. But it's like a very special, narrow corner case of data dissemination. It works actually really well over a variety of network conditions, but we already talked about why things can work that way, and that's because it's really, really slow. But it is a good least common denominator, right? They're MTU sized, under 1500 byte UDP packets. You can send them over IPv4. IPv6 is never going to happen, people. I'm sorry to tell you. This is always going to work. But it's also really, really expensive. So every message is a transaction. Arguably, this is a really, really nice thing. It lets you build reliable, distributed state machines. Every packet is a transaction. It's like, how much do you really care about packets? It has really, really, really strong invariance. And the model is a total mismatch. For our current application model, and also for the future application models that we're thinking of to take further advantage of data dissemination. So it's a really, really strong, perfect castle in a place that nobody wants to live. And then we use these transactions not only to tell our sponsor, or in fact our galaxy, where we are, but to keep a stateful firewall NAT pinhole open to them. which means that we perform these transactions every 25 seconds. It's illegible. You look at the packet, all you can see is the source and destination ships. You can't correlate packet to the message, you can't correlate the acknowledgement to the packet, right? So it's a transaction. Every packet elicits an acknowledgement back. The acknowledgement for the last packet in a message is the end-to-end acknowledgement, which means the message was processed. There's all this structure here, and it's completely illegible. All you have is blobs at the network level. You can't do anything with it. You can't prioritize based on flow. You can't correlate them. You can't route them differently. You can't say, this one I care about low latency, this one I care about throughput. No way to do any of that from the network itself. It's theoretically transport agnostic, but all you can do is what it does. In practice, it's UDP over IPv4, fixed size fields, very, very constrained. So when I started thinking about this in detail, I really wanted to figure out, could we run AIMS over Finet? Could we just take the network we have that we push everything through and rejigger it so it has all these nice legibility properties, and so you can correlate things, and if people happen to ask for the same thing, you know, they get it multicast efficiently. If packets are dropped and they ask for them again, it hits a cache somewhere in the middle of the network, and you can do it. But it's silly. So to poke, right, to send a message to you, I send a request asking you to acknowledge the message that I sent to you that I haven't sent to you. And you notice I haven't sent you the message, and you're like, oh, I can't answer his request for the acknowledgement because I don't know what the message is. So I'll go ask him for the message. And then I send you back the message in response to your request, and then you're like, okay, yeah, sure, I got it. And like this totally works. It's completely legible. It has all of the nice data dissemination properties we spent the first half of this talking about. But it's double the number of round trips. It's double the number of packets. What else did I write down about this? Nothing. It's just silly, right? It's elegant. You take two things that are very different and you turn them into one thing that is very, very simple. It's very compelling to be able to do that and build everything out of it. But it's like, you know, urbit is the slow computing movement. But there are limits. Where am I here? In addition, to it being cartoonish to double the number of round trips and acknowledgements when you do this naively, you have to sign and verify, right? So the packets are already ciphertext, but now you're attesting to them globally, and I just showed you how long it took to sign the number 0. This will take longer. But we talked about this for a while and came up with a model that I think has almost all the nice properties of the trivial toy dissemination model there, but it actually doesn't pessimize almost anything of the things that we're doing, and it unlocks a bunch of new possibilities and capabilities. So I want to run through the model. We're going to have to sort out the names, right? We have AIMS and Finet. If we're unifying them both, are they AIMS? Are they Finet? Are they something else? I called the messages the obvious things that came to mind, but like there's already names for some of these things in different contexts. These names officially come from other contexts. So peek is the Arvo's interface to read from the namespace. Poke is Arvo's interface to inject an event. These are named, you know, out of homage to BASIC. And then page, I said earlier, page is the marked data. And so it's actually like completely absurd to call this page because this is the path and the marked data and the signature that binds them all together. And anyway, I apologize for using perfunctory names, but they're what's there. The idea is a single request protocol, message-oriented. So it subsumes Finet. Peek and page are Keen and Tune This is exactly the same. But poke subsumes aims. So we have stateless read request, stateful write request. They both elicit the same kind of responses. It is a one-to-one request-response protocol. The correlation between request and response here is as trivial as it can be. It is an exact match. No funny business with path prefixes and anything like that. The poke write request is the pattern that we described, but it's concatenated down into one thing. So it is a read for the acknowledgement plus, I did something to my audio, plus a response to the read for the payload. So formally, I'm saying, can you produce an ACK for this message? Oh, but by the way, here's the message. And literally just sticking them together. So it has the same semantics, but it also has the same number of round trips. It's message oriented. This is a big difference from AIMS. AIMS actually encrypts packets individually. This was a reasonable decision because you want the packets to be resendable across rekeys. And we needed, for various reasons, to encrypt packets up front. But what that means is that in AIMS, you don't really have like a clean, stateless transition from the packet level to the message level. We want this to be really dumb. The packets matter, but they don't matter too much. The messaging layer is primary. The messages are public. And packet authentication is derived through a tree hash or possibly self-attestation if it's content addressed, but derived from the message itself. What the packet says is, I am part of this message, you have a signature for this overall message, and a root hash, and so you can trace down through the hash tree and find that I'm, the fourth fragment over here, validating it with hashes each individual step instead of producing lots of signatures and paying the cost of verifying them. But we still want packets to be specified. We need a least common denominator. We want it to be practical to run minimal run times that don't need a sophisticated I/O layer to talk to the network. So the packet level exists, it's in Arvo, it's sort of on by default. But the idea of specifying the message layer as primary is that if you have a better way to talk, you should use it and just bypass the packet layer entirely. Now again, these are public messages still, so let me check on the time. I already said they're concatenated together. One additional optimization that we can perform, because simply taking the read and the response and sticking them together to make a poke, you'd still have to sign it. And if you read it, if you unrolled those operations and performed them individually, in the model that I'm proposing, it would be signed. But everything has a name on it, and the name can be as precise as it needs to be. And so the idea is that if the message, if the payload of the poke fits in a single packet, you also elide the signature. You concatenate it together under a slightly different name, and all you need to send is the authenticated encryption that we're already using, because in fact, this is formally the two-party conversational case of the data dissemination. There's no reason to attest to it to anyone else. Now, if the message doesn't fit in one packet, you want to sign it, because signing it is the means by which you will validate all of the other individual packets that make up the message. And so when you get a poke message like this, it always includes the first fragment of the payload. And so that tells you where you can go to get the rest of the data and how big it's going to be. And when you do that, you get some real surprising benefits that I actually didn't model. I was looking for the legibility, I was looking for flexibility, I was thinking about transport agnosticism, these kinds of things. Can we pull the layers together? But when you factor things like this, the total number of writes, event log writes, involved in sending a message, an AIM-style message, where it's a command, it's being pushed from one ship to another. It's reduced by the number of fragments minus 1. We go from 2 times the number of fragments, and a fragment is 1 kilobyte, to the number of fragments plus 1. And on the publisher side, on the sender of this command, the writes involved are reduced to 1. And so this actually really, really matters for the Gall subscription model. In a Gall agent, in Gall's world, a subscription is one thing, and there's just a set of ships attached to it. But when you just step over the line from Gall's world to AIM's world, that's in conversations. You're having a separate conversation with each one of those ships. Nothing is shared except the actual data, but the identifiers aren't shared. It's not legible to the network. You do all the work over and over again, and then you communicate in this model where every message is a transaction, every packet is a transaction. The message itself is routed as a first-class citizen. The acknowledgement is routed back as a first-class citizen. There's lots and lots of overhead here. And the subscription reform model and pushing everything to FinA and having a new application model that lets user space meaningfully populate the namespace solves all of that in like an absolutely ideal way. But it's a big lift. It's a lot of changes. It'll involve rewriting applications. What can we do in the meantime? This is a pretty big deal, and the amount of a big deal that it is very obviously scales up with the size of the messages, which is kind of funny because normally we wouldn't want to encourage you to send really big messages, but so the publisher pushes out this poke message, whether this is like a plea command or a boon response to a command. They're all the same thing by the time you get down to this layer. And regardless of how big the message is, it does not have to do anything else except maybe resend that one request. The receiver of that message looks at it and sees, is there more data missing? Do I need to go out and get more data? It reads it from the publisher. Those reads don't hit the event log. When the interpreter can be parallelized, those reads will be run in parallel. If anybody else happened to have read it beforehand, it'll be in cache, all these kinds of things. In the Gall model, that won't be because each one's under a different name. But even so, those are a couple of really substantial wins that just kind of fell out of looking for legibility at this layer. And we do all of it with no additional network round trips, and for small messages that fit in a single packet, no signature overhead. Popping the stack here. We need to optimize FinA. It's too expensive. So we talked about the Merkle hash model. And I do apologize that I did not prepare a diagram. I will take just a couple of minutes and try to describe this, and you can visualize with me. So picture a complete binary tree. That means, for whatever depth the tree is, all of the branches are completely filled in. The tree is hashes, Merkle-style hashes, where the hash of a node is just the hash of both of its children. The leaves are the data fragments. We're going to send the data fragments in order, the leaves of the tree. And to each one, we're going to attach the next hash, the next best hash that we can so that they can validate things in order. In the tree, that is a pre-order depth first, left to right traversal. So you start at the root, and then you go to the left child, and then to the leftmost child, and leftmost child down to the leaf, and then you go back up to the first right branch that you didn't take, and so on. What this means is that we can validate every fragment individually, so long as we validate them in order, and we have to accumulate a few fragments up front before we can start validating, because you need the complete path from the root of the tree down to the first fragment before you can start validating anything. Now, you can validate each additional link in the path, and you start with a hash of the assigned root hash, and then pairwise hashes. And so what this means is logically you have two sequences that are multiplexed. You have a sequence of the fragments of the message, and then you have a sequence of the hashes in this traversal order, and if as you receive them, you collect them into the appropriate data structure. Once you've received log2 of the number of fragments, then you'll be able to validate each individual one after that, so long as you process them in order. Maybe this can be improved. There's a certain amount of overhead in the data here, but this is pretty nice. And one of the things that I really like about it is that it's a nice incremental step towards transport agnosticism or informal depacketization, right? Everything is really legible here. So Arvo emits the first request, right? You get that back. Ver could just step in and say, get back the first response. I'm just going to start spamming out more requests. I'll do my own congestion control right here. Maybe I won't inject any of the fragments as events until I've gotten to log2, so I don't inject anything that can't be completely validated. Maybe I won't inject anything at all, and I'll just validate the whole message and inject it in as a message. But there's lots and lots of nice waypoints along the way where we can build these things, and they're locally useful without like heavyweight, complicated designs. So I talked about the transparent multicast. The idea here is that for an intermediate node, request comes in, it occupies a little bit of state for a short period of time. If another request comes in for the same piece of data, it joins that first request and it stops there. It doesn't transit upstream. And then when the response comes back, the response is multicast out to the requesters. Really compelling for anything that anybody's going to ask twice. Maybe not so compelling if it's only ever going to be asked once. So maybe you do it, probabilistically. Like I said, this part of, there's questions about exactly how worthwhile that is, except for relatively narrow categories of high fan-out data. I still think that the model is the right model because of these other benefits from legibility. And it might even be worth it even if we don't multicast all that often. But it's worth calling out. Right now, we can forward statelessly. In this model, you can't. Very similar kind of cost-benefit analysis. Any node in the network can cache, poisoning the cache. Then all of a sudden, it's not so cool, right? So you say, well, everything that goes over the network can be authenticated, everything can be validated, but it's really freaking expensive to validate everything all the time. You just can't have a practical relay system that does that. So there's all these models of, this is a problem, that comes straight from India and it falls out of the design. And they have different models of probabilistic validation. And if you get a bad value on a request, the next time you issue the request, you put a digest in there as an exclusion, right? Like, I'm asking for this thing. Last time you gave me this other thing, it's garbage. Don't give me that garbage again. I still need that thing. Those are options. A really dumb thing to do is, our relays are going to be full nodes. Only cache the things you've actually validated. You can transit the other stuff through. It's really easy. We can do that today. We can think about the hard stuff later. We already talked about quality of service. The message orientation, the way I'm thinking about this, again, this is the public message layer. So if you're sending encrypted data, these messages are ciphertext. This is a practical, granular story around transport agnosticism. It's request response. If you happen to know that there's a gateway somewhere, you can do the request response over HTTP. If you happen to know that a socket is available, you can stream the whole message body, response body, without packetization, back over it. And you can make that decision at any point in time. You don't have to make it for the whole peer, or you don't have to make it for everyone that you're communicating with, or anything like that. Again, this is just this trivial point. The intent is legible in the data. The network can do more for you. And then we talked about informal depacketization and congestion control. Now, this is something that Ted only just talked me into like a couple of days ago. And I have been really reticent to look at message-oriented network protocols that completely bypass the authentication layer or the encryption layer, because I worry about not having something that's one thing, but just having an agglomeration of things. And it's like, well, what's the urbit network? It's like, well, there's the urbit UDP network, and here's the urbit WireGuard network, and here's the XYZ, right? And it's like, are we really gaining anything from this if we actually just agglomerate things and we pay the full complexity of the Cartesian product of all the things that we support? It's like, yeah, maybe it's still worth doing if the wins are big enough, but it's very unpleasant, very inelegant. But if you think about what I just described here of the public message-oriented layer living in the namespace, again, this is ciphertext, this is signed. And if you can lay out the names properly, and this is fairly trivial, then the packet messaging layer is in the namespace as a pure overlay of that messaging layer. What do you append? It's like fragment, whatever, or something. You know, you just kind of extend the path, and there you go. Now it's the packet namespace. It's the same thing. You don't have to materialize those packets in your state. It's a computed, you know, non-materialized view over the messaging data. But if you can lay the namespace out correctly, and this might be tricky in some circumstances, but in some circumstances it will be straightforward. You can just extend that and say, well, the true data layer, the true messaging layer, the deepest, most meaningful names is the private messaging layer. It's not encrypted. It's the actual names that you would use in your applications, the actual data that you would use in your application. The public layer, the encrypted layer, is a pure, non-materialized view. It's computational projection out over that, and the packet is another layer on top of that. And you don't really have any complexity. You've just specified these things as pure functional derivations of the base thing. It's not the most efficient thing in the world, but is Matt here? Matt. Yeah, you know what I'm talking about. Persistent memoization. Matt's going to tell you all about it. It's going to be great. It's the solution. I'm really looking forward to it. So then if you've specified this in 3 layers like this, and you come up with a trusted channel, right? You can punch all the way through without really any additional complexity. You can map backwards through the namespace, through the layers, just by convention, to actually get to the raw data. And so if you are Aqua, right? That's what you want to do. You want to pass a pointer to the data as it's persisted in the other ship. Aqua is a cool little Gall app that is a virtual bear, and it means that you can run a bunch of ships inside your ship. Right? You have homoiconic system, we have metacircularity at every layer. It's kind of a toy right now because of runtime limitations and because it hasn't needed to be really much more than a toy. We've used it for integration tests, right? Spawn up a bunch of ships and have, you know, so it's got a software-defined networking layer, and then, you know, it overlays its fake I/O drivers onto your real I/O drivers. And in some ways, this is hilariously inefficient. But if a ship isn't too busy, it really might not be. But similarly, if you're in a sophisticated hosting environment, right, and you have your own software-defined networking, you have your own channels, you have some mesh that connects the nodes, or maybe it's not your entire hosting environment, maybe it's just this particular VM, right? You know what all of these ships are. You just pass the data. It's not even going to escape. So this has always been a goal. I haven't really known how to accomplish it. I think that this is a relatively low-cost way of accomplishing it, and I'm excited about that. So here, this is a really dumb thing, but it's actually one of the things that we started with. I mentioned it earlier. Really important meta point. The internet is actually request response. Not the web, the internet itself. In the presence of stateful firewalls, I can't send you data unless you've sent me data first. And what is it trying to do? It's trying to jerry-rig request response semantics on top of this arbitrary packet network. Cool thing. If you actually model your overlay network as request response, like you don't have to jump through extra hoops to do that. You're going to play well with the direction of everything. And again, IPv6 isn't happening. You don't have to worry about it. But even if it were to happen, it would still have stateful firewalls. So it's not purely a NAT problem. And in stateful firewalls and also in NATs, those bindings, you send out a request, so now somebody else can send you a response. They tend to be pretty short-lived, around 30 seconds. So if you're behind a NAT, you got to ping all the time. Here's back of the napkin math. If it takes 5 milliseconds to process an event, and every ship is pinging every 25 seconds, then if a galaxy only ever processes pings and does nothing else, maybe it can handle 5,000 ships. So if the network only processes pings and does nothing else, maybe we can run, 1.2 million ships. It's a joke. Tlon ran into this as an actual scaling limit this year. And so the ping app now has a no NAT option, which is an emergency bypass, and it just turns it off completely. And this is totally fine, if you know exactly what you're doing and you're really, really sure that you're not going to screw it up. Because if you did screw it up, the ship just falls off the network. It's completely not discoverable. But the solution here is just not in any way rocket science. There's two different things that are being, two different roles performed by pinging here. And one of them is this discoverability problem, right? If your route changes, you have to tell whoever's going to forward packets for you, because how else would they be able to forward packets for you? They have to know where you are. But the route maintenance is completely orthogonal. And so what we're going to do is we're going to use stun, not by analogy, but the actual stun protocol for route maintenance. This is a nice, easy little win. We can say your urbit is a stun server. The stun protocol is the most trivial thing ever. And then we're like one step closer to supporting WebRTC out of the box. And all it's doing is pinging back and forth. When you get a stun request, right, what it says is, what does my IP address look like to you? And you take whatever address you heard it from, you write it down in the response. You actually have to mask it out because NATs are really dumb. And if you don't mask it out, they'll rewrite it not just in the header, but actually in the response. And you send it back. And so what we do is we establish the route in the same way that we always have, through a formal ping. And then once it's established, we maintain it with stun, and we save the response, and we compare it each time. Has it changed? Have we moved or have they moved? Have we moved or have they moved? And if we stop hearing stuns, we fall back to formal pings. If we get a response that's different from whatever we had saved, we send one formal ping. And so it's, no NAT without the operator overhead. And then in the course of the research for this line of effort, we came across a couple of things that are immediately actionable. I don't know how soon we'll be able to get to them ourselves, but I wanted to mention them here. If anybody wants to do this, come and talk to me. So there's been a long-standing problem where urbit is actually really crappy. Communicating on a local network or communicating on the same VM, you can get into situations where if you put a moon next to your planet or two moons next to each other or something, they just won't communicate with each other. It's possible that that's your not NAT, not supporting hairpinning, which is where you send a request out to this public address, but the NAT realizes, oh, that public address is me, and I actually had allocated that over here, and so it just hairpins in the NAT and comes back around. But like everything else, some support it and some don't, and it's a pain. But you can use MDNS, which is used in a bunch of zeroconf protocols, and that's just DNS without a server, to just like chat over the local network and be like, hey, I'm such and such. And then you can listen for, hey, I'm such and such, and you just like send directly to them. And there's a couple of open questions, but they're tiny implementation details. Anybody who wants to do this, I'm dead serious. We should absolutely do this. This would be great. And the other thing that we can do for real whenever we want to is actually real NAT traversal. And I can say what that is in a sentence. Not what we do right now. I'll leave that a mystery. But real NAT traversal is you have a side channel to talk to somebody. Each of you figure out all the possible inbound routes to yourself that you could discover. You exchange the sets, you try them all, you pick whichever one works the best. That's it. Again, not rocket science. And that's it. This is going to be our top priority for the network immediately. Questions?
Hey, you hinted at it a couple times, but could you say a little more about what the implications would be for running urbit on a mesh network?
That is a good question. I can't. It's a great question. I'd have to think about that. I haven't thought about it at all.
Yeah, cool.
So what's the timeline on all this?
You'll have to ask my boss.
Soon.
I'd like to hear that soon, Tian. Can you explain more about the, sort of the caching as it pertains to the verification or like depacketization and kind of with this new kind of like Merkle strategy?
So there are two different kinds of things, I would say. Edge nodes, originating edge nodes, publishers should obviously cache, and there's no trust concern there, right? They produce the data, they'll keep it available, in a way that's easy to deliver, no problem. Relays can cache anything, but you have this poisoning problem. Poisoning problem probably stems from a routing attack, so how likely it is depends on your routing model in some more detail, but it's still kind of a nasty corner case. And I'm not sure that the intermediate caching is worth the risk or worth the complexity of this like hash-based exclusion model on the requests. So what I would suggest is our relays, in this model it's possible for a relay to be, a normal program with ephemeral state. It doesn't have to be an urbit ship. It needs some metadata. Part of the goal is to get the exact metadata that it needs precisely delineated and minimal, where right now it's like the whole PKI. So for now, while relays are full nodes that are making their own requests, what I propose as the model for now is they only cache the responses to requests that they sent themselves, and they only cache them if they actually process them successfully. So you just take a subset of the traffic that goes through and say, I verified this subset, so I'll cache it, and push the rest of it down the road. The depacketization thing is much dumber, right? So like a request goes out, it's emitted from Arvo, it gets to Ver, it's going to send it over UDP, or it's going to send it over HTTP, or it's going to send it over WebRTC, or whatever. It's just a request, it's a path, it's screaming the path out into the void, hopefully in the direction of the actual ship. When it gets a response, right, the response contains the fragment number and the total number of fragments in the message. So it's easy, really easy for it to issue the request that it needs. It's just incrementing a sequence number. And it can do congestion control and open that window as wide or narrow as it wants. And the relationship of the fragments to each other comes from this hash tree. So it can say, here's everything reassembled. It all matches the hash tree. Here you go, Arvo. Arvo just verifies the signature.
And when you say reassembly there, like, is this all like one ship that is doing the verification for each of the different fragments? Or is this a distributed process?
Oh yeah, no, it's local. You got to do, who you trust is your own business.
Do you see any reason why we couldn't distribute some of this and kind of do like...
Yeah, you could. You'd have to do it over a trusted channel, right?
Yeah. Like maybe if you had like an incentive layer to prevent like cache poisoning or something.
That part, I'd have to hear more ideas about. It's not immediately obvious to me. But if you had a WireGuard connection set up to your star, and your star is like, hey man, I'm going to verify everything for you, and you're like, oh, that's great. I'm running on a potato, and I really trust my star. You know, sure, totally.
Gotcha. Thanks.
Any other questions?
Is the thing about the persistent sort of memo cache, like with respect to like what exactly?
Okay, yeah, so I'll elaborate on this just a tiny bit. I'm not going to steal Matt's thunder. We have memoization in the interpreter right now. Knock is a formula computed against a subject. Barring some really nasty corner cases that we should get rid of that we're not going to talk about and are just details of the virtualization layer, it's totally referentially transparent. You know, you get a subject formula, you're always going to get the same result from that. So there's a hint that you can pass to the runtime and tell it, memoize this computation, which is before you run the computation, check and see, do I already have the result for this subject and formula? If you don't, you compute it and you stick it in the cache, right? If you do, you produce it from the cache. That cache is very short-lived. It only stays in one virtualization context, again, for those really nasty reasons that I don't want to talk about. But if you can make it live across multiple events, now you have a really nice model where instead of materializing all of your pending packet queue in your state, you just express your pending packet queue as a function that traverses the message and jams each of them and encrypts them and all of that kind of thing, and then you memoize that. And if you ran out of memory on your VM, it's free to throw that cache away and say, I'm going to trade time in the future for space now. I'll recompute this data when it's asked for.
Okay, yeah, I was thinking like kind of maybe like in the other direction where like if you're like verifying the signature through the event loop, what the runtime could do maybe is like
you can prime the
auto
cache.
store,
Yeah,
and then
totally.
and then maybe like the jet for decrypting then just like removes it because you're not going to verify it
Yes,
again.
very much in favor of like special cased caching like that. Some other time we'll talk again about how we want to do parallelization through, cache priming, thunk replacement kind of thing.
I had one other question, which was like maybe a bit more detail on how like the poke requests are like a peak and then a page, I think is what is
Yeah,
that?
so the peak is just a path, right? Encoded, packetized. The page is the response to the peak. They're always one-to-one, so you can't like request the whole message and get back a whole bunch of fragments in response. You request the first fragment, you request the second fragment. It's all one-to-one. The poke is the request for the acknowledgement, first fragment of the payload. So the request for the acknowledgement looks just like the peak. It's just a read at the path.
Okay.
It's unauthenticated. The data itself, the payload, is authenticated. It's a response to a request for the message, right? And you just short circuit the round
I see what
trips.
so you don't have to do the round trip because you already start sending the poke
Exactly.
before they
and you
request the
just squeeze the
acknowledgement.
packets together.
Got it.
And if the paths are too long to actually fit the packets together, you can temporarily bind a content address name and send it that way. So even we can always fit this into, the de facto 1500 byte MTU.
Can you explain that part a little bit more? Like if you're handling like something big.
Well, so IP is like variably sized and all this stuff, and the minimum size is formally like 68 bytes or something, and the maximum is, it might be 4 gig. There's like jumbograms in IPv6 or something. But it's all totally fake because it all goes over Ethernet, and an Ethernet frame is 1500 bytes. And so the MTU, the maximum transmission unit of the internet, is 1500 bytes. And anybody who tells you anything else is lying to you. So your packet has to fit in that. And we have to fit a lot of data in these packets, right? This is the downside of this progression that Van Jacobson is talking about, from data being implicit in the topology or the connection to explicit in the data, is that you've added overhead. You have addresses. A lot of overhead here. We've got paths, we've got signatures, we've got hashes, right? When we're sticking two together, we have a path for the acknowledgement and a path for the payload and a signature for the payload and the data of the payload. The fragment payload is always going to be exactly, no more than 1 kilobyte. We need to have a model that lets us fit a whole kilobyte in there, that lets us index into the message in a very dumb, stateless way. We don't want to have some kind of sliding window there. So if it's too big to literally fit the packets together, right? Just take the payload, rebind it under a short name. Say the name of it is, it's just a hash, right? And you can tombstone that anytime you delete it away, a request for that won't resolve, and you fit it back in. It's done. It's fine.
Got it. Thanks.
Any other questions? No? Let's give it up for Master-morzod, everybody.